This is the second part of Chapter 2. It's covering Concept 2.2, dealing with atomic structure. So moving on to the model of the atom, and we're looking at the basic subatomic particles. These include the neutrons, protons, and electrons. The uncharged neutrons and positively charged protons are packed together in a dense core known as the atomic nucleus. Negatively charged electrons are attracted to positively charged protons in the nucleus. The electrons move rapidly at the speed of light in the space around the nucleus, forming a cloud of negative charge. Neutrons and protons both have an approximate mass of 1.7 times 10 to the negative 24 grams, which is equal to 1 Dalton or 1 atomic mass unit. Electron mass is about 1/2000th of a Dalton, and when you calculate total mass of an atom, you just neglect that tiny mass. So elements differ from each other in numbers of subatomic particles. The element's atomic number is the number of protons, and the number of protons is what identifies an element. If you change the number of protons, you change the element identity. So atomic number, number of protons. The mass number is the sum of protons and neutrons. The mass number is the total atomic mass, because the electron's mass is negligible. We talked about that in the previous slide. So you can equate atomic number with atomic mass. All atoms of a particular element have the same number of protons, as I said, or atomic number. And this atomic number is written as a subscript to the left of the elemental symbol. As you see here, sodium has 11 protons and atomic number 11. At the ground uncharged state, an element's electrical charge is neutral, so the atomic number also is the number of electrons in the atom, because you need equal numbers of negative charge to counteract the positive charge. The mass number, written as a superscript to the left of the element symbol, is the sum of neutrons and protons in the nucleus. In this example, the mass number of sodium is 23. That corresponds to an atomic mass of 23 Daltons. This sodium atom has 12 neutrons, and you calculate that by subtracting the atomic number, or the number of protons, from the mass number, the number of protons and neutrons. So that's 23 minus 12 is 11. I'm sorry, 23 minus 11 is 12. Moving on to electrons. Electrons have special properties that define the chemical reactivity of elements. So electrons that are moving around the nucleus, they have a potential energy because they are arranged in space around the nucleus, and they have a opposite charge to the nuclear positive charge. So this creates a potential energy. This is because of these attractive forces, and it takes work to move the electron further away from the nucleus. Because they are attracted to each other, it's going to take work to pull it away from that attractive force. So the more distant an electron is from the nucleus, the greater the potential energy in the electron. So electron potential energy is quantized or packaged in fixed amounts in space around the nucleus. An electron having a certain level of potential energy is like a ball on a staircase. The ball can have different amounts of potential energy depending on which steps it's on, but it can't spend much time between steps because it's unsupported and it will fall. So similarly, an electron's potential energy is determined by its energy level, distance from the nucleus, and resides between energy boundaries or shells, and these are represented by these boundary lines. and it cannot exist on those boundary lines. It's only between these lines. And the closer this region is to the region is to the nucleus, the lower the potential energy. So you gain potential energy as you move out through the shells. Electrons associated with atoms are contained in the shells, and these shells have a characteristic average distance from the nucleus with a corresponding average electron potential energy. The first shell is closest to the nucleus, and electrons with this shell, they have the lowest potential energy. The electrons in the second shell are further away, and they would have more potential energy, and as you move further out, the electrons have higher and higher potential energy. An electron can change shells, so it can move from shell to shell, but only by absorbing or losing an amount of energy equal to the difference in the potential energy between the old shell and the new shell. So if you move from this shell out further to higher potential energy, you require energy for that to happen. If you move from a higher shell to a lower shell, you're going to lose energy in some form, usually thermal energy. In photosynthesis, that would be an example of where sunlight energy can excite an electron to a higher level. There's other cases where an electron can lose energy and it'll fall back to a lower shell. In this, an event happens with that, an energy release, and sometimes that's heat, sometimes that can be a photon, a light, energy, color, etc. So alright, so there's a filling order of these shells, and this is what defines elements, this is what defines the periodic table. The chemical behavior of the atom is determined by the distribution of electrons in the atom's electron shells. So starting with hydrogen, we construct atoms of increasing mass by adding one proton and one electron at a time. And this figure is representing the first 18 elements in the periodic table. So they're arranged in rows corresponding to a number of electron shells in their atoms. So if it has only one shell, that's the row 1. If it has 2 shells, that's row 2. Row 3 has 3 shells. Okay, and then the left to right sequence, moving left to right, each row represents a sequential addition of electrons. So if you look at this, you're gaining one electron at a time until the shell is complete on the far right side. So back to hydrogen. Hydrogen has one electron in the first shell. Helium has 2 electrons, and this shell is considered filled because the first shell can only contain 2 electrons. Atoms with more electrons than helium must start using higher energy shells because the first shell is full. And these higher shells, second shell, third shell, and so forth, all can hold 8 electrons per shell. So if you look at lithium, it has 3 electrons, and 2 of those are in the first shell and 1 is in the second shell. And if you move all the way across, you just left to right, you add electron at a time till you get to neon. And neon has a completely full second shell which holds 8 electrons. Chemical behavior depends mostly on the outermost shell. So these outer electrons are called valence electrons, and this outer shell is the valence shell. So with lithium, there is one valence electron. So again, lithium, there's one valence electron in the outermost shell. And electrons with the same number of electrons in their valence shells have similar chemical behavior. So if you go down the list here, fluorine, for our example, fluorine and chlorine behave similarly. In fact, they both can form compounds with sodium in the form of salts. So an atom with a valence shell completely filled with electrons is chemically unreactive or inert. And this is represented by this far right column where all the outer shells are filled up. And so they're chemically unreactive. That means everything else can react because their outer shells are not filled up. One other thing to note here is as we're filling up the second and third shells, moving from lithium, you move to beryllium. Instead of pairing up with the first electron, it's a loner. It goes by itself, and that happens all the way to carbon, where you have 4 unpaired electrons. They fill up first by not being paired. Once you get past 4 electrons, they start pairing up. In the case of nitrogen and oxygen and then fluorine. So they fill up after that. That's an important thing to know. It helps you determine chemistry. And with that, that concludes this mini lecture for Concept 2.2. Thank you.